It's my great pleasure to introduce Lenka Zdeborova from EPFL. Lenka is a professor of physics and computer science at EPFL, where she leads the lab of statistical physics of computation. She has many great works that use statistical physics tools to machine learning problems, including a series of impressive contributions to the foundational understanding of over-parameterized machine learning. Lenka's talk on insight from solvable models to over-parametrization is going to be an excellent start for our workshop. The stage is yours, Lenka. Thank you very much.
Thank you, Yehuda. You put the bar high. But yeah, thank you very much for organizing this. And I see some familiar names in the audience in the panel. So it's good to be with you, at least like that virtually. So I will try to do some kind of overview of the kinds of works that we did in my group and close collaborators on this topic. Yehuda made a wonderful overview. So I'll add to it a little bit the way I like to start talking about heavily parametrized neural networks or over-parametrization is to show you this citation from Leo Breiman's paper from 1995 that shows us how old that question actually is, and it's still standing. And I will give you kind of my vision on that. So that's the first of these three Breiman's questions. They're all really interesting, but this workshop focuses on the first one, so I will focus on the first one. So how comes that already in 95 he was asking that? So one thing is that the very paper that in a sense is the paper that one cites when talking about bias variance dilemma that introduces this U-shaped curves as seen here for k-nearest neighbors. That's what many of us teach our students. There is actually figure 16 there where they do the same thing as a function of the number of hidden units. They plot the test error of something, I forgot what, being learned with the neural network. And they see indeed that there is not the U-shaped curve, that it's a curve that keeps going down. There's not a peak because I suppose they early stopped or over-parameterized or regularized. But already in that classical paper, we kind of saw the core of the mystery. How comes that the test error keeps going down as the number of hidden units is being added? And then, as Yehuda said, I come from physics. So me as a physicist, I saw those curves of learning. And this is actually not, in a sense, here these are single layer neural networks in the papers coming from the early 2000s. So the over-parameterized regime is not on the right as you're used to see it, but on the left. That's where the number of parameters is much smaller, or much bigger than the number of samples, or bigger than the number of samples. So in a sense, you don't have this decay as you are more and more over-parameterized, but you see the peak. You see the peak in the ridge regression, and you see some kind of a peak in the I forgot whether this is the max margin or the logistic regression. And there are whole books written in statistical mechanics about how to actually, this is not an empirical curve, this is an analytical curve, how to actually get them. And this is where kind of statistical physics entered this question already a long time ago. And then in the more recent developments, I mean, these two pictures also come from physics origin papers of colleagues, Andrew Sachse, Madhu Advani, and Mathieu Viard's group, where on the left-hand side for classification, on the right-hand side for regression, they kind of put this double descent curve into evidence, all that kind of before this classical paper that, this picture, I think most of you, or all of you probably have seen from the Belgian's paper. So you see that the kind of physics part of this story is kind of well interlinked with the question. And I like to say that understanding deep learning is also a job for physicists. That in Nature Physics, let me write the comments about that. So what I want to do in this talk is walk you in the classical results from statistical physics and then the more kind of recent ones. So this walk in the classical results, that will be maybe the next 20 minutes, will be on the case where we actually do not have hidden units, so do not really have over-parametrization, but that will kind of set a stage to then looking at the over-parametrized models, and then on the kind of random features and kernel ones, and towards the end, can we actually go beyond that, or how to go beyond that. So the kind of model that we love to study or set in most of the statistical physics literature is the teacher-student model, where we actually abstract away a lot of the complexities coming in some real task on some real data, but I will be coming back to that, how to kind of go beyond towards the real data, where the labels, so the teacher network is fed random IID vectors X, and they are not only IID sample from sample, but also the components are assumed to be IID. And then this is fed into a teacher neural network that has weights that were chosen by the teacher in some way at random, for instance. And then the teacher neural network generates outputs Y. And then the student network, that's the model that is learning, has access to the pairs of inputs, outputs. And to simplify, because that can only simplify, not make things more complicated, the architecture of the teacher network, but not the values of the weights. And then the task of the student network is the classical one. Can it learn the function from X to Y so that it's the same function as the teacher was using from a limited number of samples? And what is then the performance on newly seen new X that was not in the training set? So the classical generalization error question. So as I said, this model has been formulated in physics already more than 30 years ago in this paper by Gardner and Derrida in its simplest form, where both the teacher neural network and the student neural network are just single layer ones. There are not any hidden units. So it's directly the input towards the output. And again, they take a Gaussian IID input and they take IID teacher vector weights, teacher weights, from some distribution PW that will be changing, depending on that, the behavior will change, and create the labels, and then ask, already 30 years ago, they asked about this challenging high dimensional regime, where the number of samples N is large, but the dimension, the input dimension is also large. And the ratio between the two of them is actually just some constant. So we have, say, 3 times more samples than the dimension or something like that. And whole books have been written about actually what's the solution of such a problem. So I just here give 3 of them again in that era. And maybe the kind of focus of at least the line of calculation that I like to present is on the base optimal generalization error. So this is something that we usually don't speak about in traditional kind of machine learning, because we usually don't know from which model the data comes from. So in this teacher-student model, we do. So then we can actually compute this absolutely optimal baseline over which no possible algorithm, whether it's exponentially costly or not, cannot improve. And the fact that the test error will not be 0 is purely given by the noise and by the fact that we only have few times more samples than the data. So that's the high dimensional regime. And what needs to be done to compute this base optimal generalization error is to write the posterior measure of what were the weights of the teacher given the pairs of inputs and outputs that we observe. And that's given simply by the product between the prior and the likelihood. The likelihood is just the product over all the samples of the probability that a given label was created by the teacher network given the input and the weights of the teacher network. And if the teacher was using a deterministic function, like for instance, the sign of the scalar product, then this probability distribution is simply a delta function. But if we had noise, we could add the noise here, and this P out can be, whatever we kind of assume the teacher to be doing. And then if a new sample is given, the base optimal prediction needs to compute, estimates a label y hat new. That is the expectation of over the posterior of the function that the teacher is using of the new sample time, and the expectation is over the weights that the teacher could be using. So this is the way to compute the base optimal estimation of the new labels. And just to contrast this to the, I will also talk about the traditional empirical risk minimization, where instead of averaging over the posterior, we actually write some loss function, maybe some regularization, and then we go on minimizing that function over the W's and then plug the resulting W into a predictor and compute the label from that, which in general does not have such a good test error as doing what I described on the previous slide. So this is just kind of a basic textbook properties, but now given that we want to analyze this base optimal performance, what these 3 books few slides back actually derived on using the replica method from physics that back then was kind of a heuristic method to derive an expression. In this paper 5 years back, we actually proved that that indeed is the right expression for the class of the teacher-student models that do not have any hidden units and that have IID Gaussian data at the inputs. But the activation function that the teacher is using can be arbitrary. That's hidden here in this P-out function. And the prior that the teacher is using for the components of the weights can also be arbitrary. That's hidden here in the expectation over the components of the V. So given those 2 functions, we actually can write what in physics is called the free energy, which is the limits of the expectation of the logarithm of the normalization of the posterior function. It's an expression that looks kind of non-intuitive. But what is nice about it is that this expression is actually a couple of scalar integrals. It's not high dimensional anymore. The limit of dimension going to infinity has been taken and the number of samples is just a constant more than the dimension. That constant alpha appears here, but the high dimensionality went away. So plotting what's the result of this expression is in principle easy. And now, okay, what is this free energy good for? That's the generating function for other quantities of interest. So notably here we are interested in the test error, in the optimal generalization error that is simply given as a, once we actually evaluated this free energy, is really just a very, very simple step to evaluate now the test error from the same expression. So that's a really direct consequence of the previous claim. Now, just one slide on how actually the math behind this goes. So to prove this formula in the setting of the base optimal learning, we needed to use the Guerral-Toninelli-like interpolation, which is a technique that was developed in the physics of spin glasses to actually prove theorems about those models. And here we needed to adapt it to this case of base optimal estimation. And we had this key property that kind of made the whole proof work, that in physics is called the Nishimori property, but it's saying that in the setting of the base optimal inference, actually expectations over the weights that the teacher is using, this W star, are exchangeable for expectations over a sample from the posterior. And that's, again, can be proven in few lines, kind of a generic property of this base optimal inference, but that is a key kind of element that if we didn't have it, this particular proof would not go through. So now having established that, we can actually plot what that formula actually tells us. So here is the most often considered example of spherical perceptron, where the teacher takes the weights IID Gaussian and the inputs are IID Gaussian, and the teacher is using the sine function to generate the outputs. So then the student observes x and y's. Y's are just plus minus ones. And here the x-axis is, as I said, the number of samples divided by dimension. You see that it's like 3 times, 4 times, 5 times more samples than the dimension. And red is the optimal test error that no possible algorithm you can think of can improve. Is just you have too few samples to be better, to be able to do better than that. The black dots is an approximate message passing algorithm, or about which I won't be speaking too much today, but that's an algorithm that actually is closely linked to these expressions, and that in well-defined regions of parameters is matching the optimal performance. And then in this case, blue, that's just if you asked your, good but not particularly undergrad student to actually take this data set and classify, they would run the logistic regression, and that's how well they would do, pretty comparably to what the base optimal performance is in this particular case. And so this is something that we found a bit striking. So we also just to tell you that there is also a similar or comparable closed form expression for the test error that empirical risk minimization would achieve on the very same task. So the data are generated as before, but this time the student is actually not this base optimal student, but your typical, say, ridge regression, logistic regression, according to what you pick here as the loss. And also for the test error of that student, we have a closed expression for the test error that this time I'm not giving in the same limit. And the proof there goes a bit differently, because now we don't have this, this Nishimori property anymore, but at the same time, we assume here the losses that are convex, in which case we can prove these formulas using the Gordon minimax comparison. And again, having the formulas, we can plot the performance. So for instance, this would be the performance on the very same task of the ridge regression with different values of the regularization. And the black line that is below, that's for comparison, the base optimal performance. So you see the ridge regression is a bit worse. In this is the same data in a log-log scale. So you see, for instance, the decay of the base optimal performance here is at 1 over alpha, whereas the ridge regression is 1 over square root of alpha. So it's a worse rate. And then you see here the interpolation peak for small values of regression. So that's really the same kind of a peak that we see in the double descent, except that here is the case with no hidden units. So here the over-parametrized regime is on the left, not on the right. Okay, I will be getting to the other case in a moment. And this is for the ridge regression. The next slide is for the logistic regression, the one where before I showed you gets really close to the base optimal. So indeed, we could see from the formulas that the optimally regularized logistic regression is essentially if I plot it in a normal kind of scale, you see no difference from the base optimal. But here I actually plot the difference between the two. And we could see, we kind of spent a month actually looking at the equations, seeing whether they are actually different, and persuaded ourselves that there is a gap between the logistic regression and the base optimal, but it's really tiny, tiny, tiny. It's like 10 to the minus 5 on the test error. So it's essentially the same. So it's kind of a curious case. So another, I want to define and spend a bit of time on an example that is another example of the teacher-student setting, still with no hidden units for a moment. But this time, this one will lead to truly non-convex. You really need to do non-convex optimization to actually learn something useful about this problem. And that's the problem of phase retrieval. And I will then be talking about it also later. So phase retrieval, broadly said, is a problem in signal processing, in imaging, where you observe typically optical signal, and that's kind of a wave, and you measure the intensity of the wave and lose the phase on the run, and then need to reconstruct it. So here, for the purpose of the talk, I will be actually, and that's because the wave can be represented via complex numbers. Here I won't be even talking about complex numbers. Everything will be real valued. And analog of losing the phase will be losing the sign of the scalar product. So I'm losing much less. So I will be looking at this kind of real valued phase retrieval or sign retrieval, if you want. Under the teacher-student setting, where again, as before, the inputs to the teacher neural network are IID Gaussians. The teacher is using IID Gaussian weights, but now is not using a sign to generate the labels, but is using an absolute value to generate this time real valued labels. And the task then is a regression from the training data and examples of these input-output pairs. So this phase retrieval the formula that I showed you on a few slides back actually applies to it. That was not specific to classification or design function, that could be generic. So in the same paper, we actually have a plot where we show the optimal test error. This is actually the mean square error, but the test error would be essentially the same curve. We have it in the papers for how well we are reconstructing the signs, or equivalently, how well we are predicting Y's for new samples X. And the orange line would be the base optimal performance. When you don't see any orange, is because it's covered by the blue, but we see kind of as a function again of number of samples over dimension, what it does. And here the approximate message passing, which is the blue line, is actually not matching. There is a gap, which is this hard phase, which kind of is a subject on its own. We believe that among the very efficient algorithms, those that would be really running linearly in the size of the system, this approximate message passing algorithm would be optimal. And there is a big effort in computer science trying to prove things about that. But that's not what I will be talking about today. What is kind of relevant for the talk today is here is just a slide on kind of how this hard phase is related to metastability in physics. It's kind of the supercooled liquid, the water at -5 degrees Celsius. That's a similar phenomena why the algorithm doesn't reach the perfect generalization in the hard phase. But what will be more important for the talk today is kind of a heuristic or kind of theoretical physics argument that we gave in this paper a few years back, which basically is saying that in the problems where we can identify this hard phase, because in this problem I was showing you is even small, like why should you really care? But you should care because this paper seems to suggest, it seems to be generic property, that when there is such a hard phase, the problem becomes actually quite hard for gradient descent based algorithms for broader range of the sample complexities. So to illustrate that for the phase retrieval, let me now try to solve the phase retrieval with actual, some version of empirical risk minimization, so some kind of a regression. I write a loss function like this. I don't really take the traditional loss functions between y and x. If I take the squares here, if I took, say, ridge regression between y and x, or logistic regression between y and x, I would actually not be able to learn anything for the phase retrieval for sample complexity that would be constant times the dimension. But this one, if I actually, in a sense, put the squares at suitable places so that, in a sense, I included in the loss function the fact that the teacher was just giving away the absolute value of the scalar product, not the actual value, then this is a very natural loss function on which we should actually be running some kind of gradient-based algorithm. So that's why I'm using this one. It's kind of to make it easier. If I was using the traditional one, it would be even worse. But even for this one, that is kind of using the knowledge that the teacher was generating just the absolute value. What is known about the gradient descent on this loss function? So in computer science, relatively recent papers, there will be proofs of lower bounds that you need that actually, if gradient descent sees d times some polynomial of log d samples, then it can learn the phase retrieval perfectly. But that corresponds to log d alpha, and d goes to infinity, so that's way too big alpha. This more recent paper actually changes the loss function slightly, and under that change, they can prove that a constant times the dimension is actually enough for the gradient descent to work perfectly. But remember, the AMP was able to learn perfectly from just 13% more times the dimension, so there is a huge gap. Might be just that the proof techniques are so far not as sharp. So why don't we just try numerical? No? So the next slide will be actually the extra numerics. You just run the gradient descent on that loss function. What do you see? You do it for a range of different sizes of the system to get actually an idea how that changes with the system size. And what I'm plotting here is a fraction of success. That means that you learned almost perfectly the phase retrieval, the function that the teacher was using. And what you see here is that actually you have success in almost all cases, but only when alpha is quite large, say 8, 7, 8. And it's actually getting worse as your size is growing. So this is compatible actually maybe with the logarithmic shift to the right. Okay, this is just numerical data, so this is kind of not so clear, but definitely what is clear is that when alpha is say 4 or 5, just 5 times more samples than the dimension, the gradient descent have troubles. It's not managing to learn the phase retrieval. So I put it back into my axis. So even if you just try empirically, there is a gap between what the gradient descent does for the phase retrieval and what actually say the approximate message passing would do, or the information theoretic transition. So then I will talk about what to do about that gap towards the end of the talk. But before going to that, I kind of recap this first part. So far in my teacher-student model, there were no hidden units, okay? And I was showing you pictures like that with what is an interpolation peak, but kind of the interpolation was on the left, not on the right. And I showed you how to analyze base optimal and ERM performance, and the input dimension here was the number of parameters. So no hidden units, then I cannot go around this. This is why. So that's kind of not really over-parameterized case. So now I want to go to the simplest model with hidden units, simplest at least from the point of view of analysis, which would be kernels or random features. So when we actually have one hidden layer, but the first layer we are not learning. And then the question is, can we get these same methods to give us a similar kind of analogous closed form expression for the test error in those cases? So that, say 4 years ago, I didn't know. It seemed like an interesting question, but I didn't know like whether we can do it. But we managed, so just to define what is the learning with random features. So here I'm in a setting where it's again the teacher-student setting. D will still be the input dimension, N will still be the number of samples. But now I have a hidden layer of size P. And the first layer weights will be called F. And those are not learned. So they are fixed at random from some distribution, or we will see they actually don't even need to be random. They can be deterministic. So, but the important thing is that they are not learned. So as long as they are not learned, and you know the kernel and the neurotangent kernel, that would be just the limit of this when the width of the hidden layer actually goes large. So I can take this parameter P very large, and this will be just a special case of what I'm showing. And so why I was saying that, say 4 years ago, I didn't know how to solve it, because we kind of did not realize, we realized only in this paper, say back in 2000 or late, 2020 or 2019, that there is a property that makes it actually that these methods can be applied very readily. And this is called the Gaussian, or we called it the Gaussian equivalence. That's a peculiar property that actually the data that are created with some non-linearity phi, and that's important for the random features to be kind of interesting, the features and the inputs C, that that actually the learning curves corresponding to learning from the X and Y like that are exactly the same in the limit that we are considering, this limit here, as if actually we took the data, the output of the hidden layer without the nonlinearity, just rescaled by some constant kappa 1, kappa start, and kappa 0, which are just some scalars related to the nonlinearity that the teacher was actually using. So this is a property that, okay, there should be maybe a longer list of papers here. We kind of, it struck us in the paper of May and Montanari in 2019 that was on ridge regression. Then the same group had one on max margin. Again, then they were not, they were using or conjecturing this Gaussian equivalence, but not proving it. Realizing that we actually could do the following. We actually computed a closed form expression. This one looks a bit scary, but you know, I just wanted to like put all the equations, but it's again closed form, low dimensional set of equations that you can solve. What we did more in that paper, that's a paper our postdocs in ICML 2020. What we did more is that we went beyond regression. The loss that for which this formula is valid is any loss. The features are fixed, not learned, but they don't need to be random, that they can be deterministic. And all that matters actually in the formula is the Stieltjes transform of the associated spectral density. And the loss function L here can also be generic, and this formula applies to these cases. So we generalized using this Gaussian equivalence assumption in this paper. We generalized the formula to this case. And then here I'm citing a paper from the group of ULU where they actually proved that indeed this Gaussian equivalence property is true under this setting. So this formula is fully rigorous as well. So now just an illustration of what I was saying, that the features do not even need to be random. So in the paper, what we took, we compared actually the learning curves that you get if you compare random features and orthogonal features. So that was kind of a curious suggestion in this paper in 2017, that actually the orthogonal projections lead you to slightly lower test error. So they observed that empirically, had some kind of heuristic theory to explain that. But here we have a solvable model where we could kind of explicitly show it, that indeed, if you use orthogonal projections, but all the other parameters are the same, you get a better test error than if you don't. And in these plots, so red would be the orthogonal projections, the blue are the random ones. It's always the test error, the generalization error, and this side is the this side is logistic regression, this side is regression, and above are the cases where you regularize but really, really little, so effectively no regularization, and below is the optimal regularization. So you see the interpolation peaks or cusps that are lost when you optimally regularize, and that's a common property that is true for both the ways of choosing the features. So that would be this case, and this is kind of back to the kind of random features, where again I'm comparing in blue the ridge regression to the red the logistic regression at small regularization, the full curves, and in dashed is the optimal regularization. So they actually look, they're almost the same curve, but the logistic regression is slightly better in this case. And on the top, that will be the test error, and on the bottom is the training error. So you see, this is one of the realizations of this double descent, where you clearly see when the training error goes to 0, you go to interpolation, you have an associated peak in the unregularized, in the learning curves corresponding to the unregularized losses. And if you regularize well, then actually this peak disappears, but the striking behavior remains that the test error keeps going down to its kernel limit when the width would actually go to infinity. So this is one of the solvable cases where we actually could generalize to more generic than random feature maps and arbitrary loss functions, convex ones, still in this paper. And this kind of is just a slide to say that here we kind of understand why this keeps decaying, where this kind of implicit regularization comes from, because these are one of the few cases where we actually know that the minimization of the square laws leads to the least norm solution out of all the kind of possible interpolating solutions. So here in this black blob, imagine each pixel would be one interpolating solution, and then there is this blue kind of dot of pixel that is the particular one that is the least norm, that's where you're actually going. And for the logistic regression, it's again a blob that interpolates starting from a different point, and there is one specific point where you have the max margin solution. That's where the very weakly or not regularized logistic regression does go. So these cases we kind of understand, and I should probably put here a long list of references where this has been established even before. Now, just 2 slides on speculation of how this actually looks in a complex non-convex landscape, because both these were convex losses. And since the first layer is fixed, it's fully kind of convex optimization problem, nothing special there. And here, I mean, that's why I chose to plot the blobs this way, because this is an actual picture from works on random constraint satisfaction problems that a priori have not much to do with learning, but actually do, because the landscape is there very analogous. And the landscape that has been analyzed in detail in these constraint satisfaction problems show you that when things are truly non-convex, that there is the kind of information theoretic interpolation threshold where you could in principle find interpolating solutions. But if you actually run some algorithm to do that, then those algorithms start to find interpolating solutions only later. And this is something that must be a very generic phenomena in non-convex setting that has been concretely characterized in these constraint satisfaction problems. And there are many kind of works on that. But that kind of remains to analyze these truly non-convex landscapes in the context of learning, where with continuous variables. Okay, I just wanted to flash this. There would be more to say, but where I want to make a point, maybe in the next few slides, is now this kind of one should be self-critical. And so far, all I showed you was about models where the input data are IID random. So that seems like, okay, why should I care? Nothing is IID random in the real world. So can we kind of, again, use the obtain similar kind of expressions, but this time for data that would be more realistic, not IID random. And that has been a line of work on which we worked in the group in the past few years, and actually came up, the result of that is a slight kind of generalization of this teacher-student setting that actually captures a lot of more interesting cases where the input data can be quite realistic. So we call this the Gaussian covariate model, comes from this paper over here at last year NeurIPS, where we actually have now two kind of random vectors, U and V, and they are correlated with the covariance matrix that is given here. And now the teacher, to generate the labels, is using the vector U, and they are Gaussian correlated. The teacher is using U, but when the student is learning, the samples that the student sees are actually the vector V, and the labels Y generated by the teacher. And these, the correlations here can be generic. What will then matter for the formulas will be the spectral densities of these correlation matrices. And what we want to analyze is the performance of a student that is doing empirical risk minimization on the samples that are the V's as inputs and Y's at outputs. And again, we have N of them, N is just a constant times the dimension. Can we analyze the learning curves for that model? The answer is yes. This is the corresponding formula for the free energy, the test error. The details are in the paper. I will not here be explaining the details, that's not possible in a talk. At least I don't know how to do that. But again, morally, we have the same results as for the simpler models that I was showing before for this generalized model. And how is that more interesting than the case before? So what does it, for instance, capture? I said it captures more realistic data. So to give you an example, the kind of synthetic input data that it captures would be data that would be generated by a GAN. So imagine that you trained a GAN, some generated network here to generate sci-fi images. Then you gave me the trained GAN, and then I would be feeding random vectors Z to the GAN and outputting some vectors X from it. And then how to kind of apply the Gaussian covariate model to this setting, it would be to say, okay, there is at the beginning, there are random vectors Z that are being fed into the generator network that has the weights it has that you gave me, and that I can examine then, compute some covariances from them. That generates data X. And then a teacher can be taking this data X and applying a feature map on them to generate labels. This feature map of the teacher can actually itself be learned. I so far am not able to describe the learning process, but if you actually did it aside, gave me the learned network with the matrices of weights, and again, let me to use it and compute, say, its spectrum, then this is fine, this is all I need. And then the student is actually taking the data, again, can be applying a feature map to the data, for instance, random features or scattering transform, or just identities, taking them as they are, and taking the labels that the teacher generated and learning on it. So that's kind of, now it becomes a bit of a convoluted setting, right? Maybe, but this now becomes something that looks like, okay, now the data that can be generated by GAN is in principle, like we believe, you know, pretty generic. So this looks way less restrictive than what it looked before. Now, up to which point it is true, that's an interesting question. But you know, concretely, this the setting that I'm describing here, that's what we did. And here the dots would be the dots of actually doing that experiment, running the gradient descent, and you know, generating the data and running the things. And the lines that would be result of the formula that I showed you before, that is using just the spectral densities of the corresponding feature maps. So you see that, okay, that kind of captures the learning curves, or in this realistic, where, you know, realistic, you can take it with a grain of salt, the setting. So in particular, you know, we get quite good agreement between that teacher-student model and its kind of analysis, which are the lines, and the actual experiment, both for the training and generalization loss. And, you know, it kind of captures when there are some cusps telling us something about the double descent, then it kind of captures its position and you know, corresponds to where the corresponding data would stop to be linearly separable if this was a logistic clause with small regularization, which here it was. So the theory kind of is able to capture more realistic data, and sometimes even real data. So here are actually 3 recent papers that we did, that each of them have some peculiar examples in the empirical sections where learning curves on actual real data, so either CIFAR or MNIST, etc., would be captured by the curves that are derived from these kind of formulas. So this first paper, that would be only for regression, that we could see such an agreement with real data. In this second paper, where we actually generalize to a model to which a Gaussian mixture is fed into the t-shirt, then we could also reproduce some real learning curves of classification problems. And in this last paper, we actually looked at the kernel limit when the width goes to infinity, and some learning rates of the kernels that, you know, we just apply to some real setting. We could reproduce them from these formulas. Now here there will be, you know, many questions. What are the exact mathematical settings under which this is true? Most of it is still open. A lot of it we are working on, other people are working on, but there is a lot to be done here. But kind of the conclusion, we can analyze the learning curves of random features, kernels, or all these learners that are only learning the last layers and fixing last layer and fixing the previous ones. And we are not restricted anymore to this simplistic IID Gaussian input data. This can actually model more realistic data. The question that still remains is, now can we go beyond learning just the last layer, right? So now let's go back to this example of phase retrieval. That's why, you know, the last thing that I want to tell you is go back to this example of phase retrieval. And now think back about it. We know from, okay, again, works that I could cite, but it's pretty kind of well known, that in order to learn to generalize perfectly the phase retrieval, we would actually need order dimension square samples if we wanted to do it with random features or with kernels or with these kind of methods that are only learning the last layer, not truly learning the features. But we also know that with, you know, Bayes optimally or with the AMP, we only need order dimension. So there seems to be a huge gap. So can we actually do better? And I also showed you the kind of vanilla gradient descent on this quadratic clause that is actually doing better, needs something like 7 times the dimension. So there is a huge, you know, we can do much better in this case if we are actually learning the features. But now, can we actually analyze such a learning where we are truly learning the first layer? And so this is still generally a challenge, but we have this one paper where we actually managed to analyze this learning of feature learning with hidden units and with this kind of minimum sample complexity, at least in scaling. The constant, you will see what is the constant. And so here is just remind you the phase retrieval, but I already defined this. This is again the teacher student. I go back to kind of the input data to be IID Gaussian. We could then combine all that, but for the purpose of these few slides, I go back to the simple setting. But now the teacher is taking the absolute value to generate the labels. And I remind you this slide where the kind of vanilla gradient descent empirically needs more samples than, say, the approximate message passing to learn perfectly. The question is, can we close this gap by doing something traditional, not going to some particular class of algorithms such as the approximate message passing? And here is where the over-parametrization comes in. So let's try to analyze learning as before on a loss that kind of has these squares here. So we kind of gave away the information that there was something about the absolute value, but this time is over-parametrized. This time it has a hidden layer, and the hidden layer actually for our proof to go through needs to be just at least one bigger than the dimension. So M, the size of the hidden layer, needs to be bigger than D. And then what does a gradient descent do in such a setting? So that's something that for this quadratic loss, we managed to analyze by combining this kind of geometric argument that is showing us, or argument, this is directly the theorem, that is telling us that if alpha, that is number of samples, was more than twice the dimension, then this over-parametrized loss has with positive probability a unique minimizer that corresponds to perfect generalization. We only managed to prove positive probability, but these things have to concentrate. If it is positive, it's very reasonable to assume that it must be 1. Whereas if the sample complexity is smaller than 2, then there are more minimizers. So a priori, we don't know to which one we go. And we also, just to be sure that the gradient descent is sensible here, managed to prove that in this setting, the gradient descent goes to one of the global minimizers. So if there is only one for alpha bigger than 2, it must go to this one. And this is just numerics showing us that indeed this is sensible, fits with the numerics. So putting the results of this paper in 2 years ago NeurIPS on my axis, we actually show that the over-parametrized neural networks trained with gradient descent needs only twice the dimension number of samples. And I remind you, this is a setting where the kernel learning or NTK or random features would actually need D squared. Whereas with the adjusted loss, these works show that large constant times D is enough. And our work shows that twice the dimension is enough. So there is still some gap between what the approximate message passing can do and this result. That's an interesting open question whether that can be closed. I don't know. And this brings me to the conclusions, kind of the high level message is that I showed you a bunch of solvable models that capture the double descent behavior for rather generic losses and structures of data or features. And I showed you in this last that this last example was an exception to the fact that analyzing the merits of over-parametrization beyond the cases where we are learning only the last layers is still a challenge. We don't have so many. If you know of some that I should have cited, please let me know. If I miss some in the literature, I would be happy to catch up. And the example where we actually could do it, and I think there are not many of those, was this phase retrieval with quadratic activation. And what we saw, it's kind of interesting speculation that I have on over-parametrization is that we saw that it helps the gradient descent in the phase retrieval, right? But other classes of algorithms such as approximate message passing, they couldn't care less about over-parametrization or not, they were still achieving this 1.13. So this to me tells that over-parametrization and the need for it, the advantage of it, is actually closely linked to the fact that we are using gradient-based algorithms. And maybe one day when we will be training neural networks with something else than backprop, because somebody will come with a super good way of training it with some smarter algorithm, maybe we won't be needing over-parametrization either. But okay, that's kind of a speculation. to just make us think forward. And here is just a list of references on which this was based. Thank you.
Thank you very much, Lenka. Thank you for the insightful talk. It is really impressive, the range of settings that you study, from simple with with Gaussian settings to real data. So it's really impressive. Any questions?
And it's always the same method in a sense, right? So that's kind of why we can study range of settings. You need to trade something for something.
So it's great. It's very interesting. Questions from the audience? Let's see. Okay, Jeffrey, you're welcome to ask your question.
Yeah, great talk. I'm curious for phase retrieval if you have any evidence, numerical or otherwise, about how SGD fares.
Yes, thanks. So I actually do have a talk on more on the dynamics, not on the over-parametrization, and that one. So there is this kind of, at least in the literature, this discussion whether actually as the stochasticity and stochastic gradient descent kind of helps generalization or not, right? And some say that it does, and there are some nice theory works about that. And then I don't know, for instance, the recent paper of Tom Goldstein would argue that no, it's not really needed in practice, and it's a super interesting discussion. So we kind of thought that the phase retrieval is a good playground to test that. And in the framework of the phase retrieval, under the super simple synthetic setting that I defined in this talk, we actually saw that it does help. And that stochasticity is another way to bring that constant that was roughly 7 for gradient descent to something like 2.5 for the stochastic gradient descent. Not the vanilla stochastic gradient descent. We had to kind of redefine the stochastic gradient descent because we also wanted to analyze it. So we wanted to have a version of it that would have a well-defined flow limit that is different from the gradient descent. So we defined something that we called persistent stochastic gradient descent. And for that particular algorithm, we could show that indeed it's another kind of mechanism how to improve the sample complexity. And then, I mean, you could, kind of thinking now forward as you probably do, you could ask, and now if I combine the stochastic gradient descent with the over-parametrization, does it get even better? And we don't know how to analyze that, but we tried numerically, and it didn't seem to be kind of enhancing one the other. So they don't kind of add up. So there are things to do. That's a really great question, and kind of analyze that more in detail. This was not, the analysis we did was based on things that were not rigorous. So definitely there is still a big gap on that side.
Okay, thank you. Are there any more questions?
Rich is raising his real hand.
It's a super interesting talk. Let me ask, just for practitioners out there, so the phase retrieval results are just really interesting, and what needs to be developed, or what stands in the way of just applying these methods, like in some kind of real optics, say, setup, right? Because it is really promising. Any thoughts? Yeah. Can your methods be applied just kind of out of the box, or is there still some work to do?
So okay, so kind of two ways to answer. So okay, from one hand, like, we are not really yet close to giving any practical advices to practitioners. But one way I like to put it is, at least to practitioners who are developing algorithms, I think these kind of synthetic settings are great playgrounds to actually show off your algorithms, right? Because instead of like taking for 1000th time the cipher, why don't one take one of these synthetic settings where you have good understanding what's optimally reachable, right? For instance, via this approximate message passing, and you don't show off your kind of new optimization technique on that benchmark, right? Can you improve here? Because if you have some algorithmic improvement that you hope is pretty generic, it should also improve on some, you know, kind of natural synthetic settings such as this one. So I like to put it this way. And there was kind of two parts of the questions. What can we say to practitioners today? So I would say this, and what is preventing us from analyzing something more realistic? So that's kind of going to this hurdle where I was saying that so far we don't know, you know, the result that I was giving you where we analyze learning of the first layer for the phase retrieval is very specific to the quadratic activation and to the phase retrieval teacher. Like if, for instance, you give me another loss function and ask me what's the sample complexity of the gradient descent, I don't know how to write the corresponding equations. And also the result in that last part was kind of, you know, it's okay. I said it's all the same method. It's not true. That method in that paper was different. It was kind of more geometric. I don't know how to write the kind of replicated free energy that would be asymptotically exact for that case. When the hidden layer is extensive, say, like the same order as the dimension, and I'm truly learning the first layer, you know, beyond kind of the kernel and decay setup. So there is, of course, the mean field limit or the hydrodynamic limit, and the results along those lines. But those are not doing the job for me either. Why? Because you end up with ODEs that actually still explicitly depend on the dimension, right? So they are not in the high dimension. You know, I would ideally like to now take those ODEs and take the dimension to infinity and have something truly low, you know, scalar. That we tried. I don't know how to do that. You know, maybe the people working on that will come up with how to do that. But that's not doing the job for me either. So all in all, I don't have a close expression for the test error, even for the synthetic settings, if the hidden layer is extensive and I'm truly learning the first layer. And if I had that, then I believe I could like chain it and make it multi-layer. But that's kind of the obstacle currently, technical one.
Yeah, super clear. Thank you. Yeah, that's great. Lots of interesting work to do.
Yes, still a lot. All right. More questions?
Yes, any more questions? We have time.
I've got one, actually. Thanks for the great talk, Lenka. So I thought that where you considered it, the joint distribution of features for both the teacher and the student, which could be having a general covariance matrix. This seems like an interesting theoretical area for exploring the model misspecification between learning and what actually generated the data. And I was wondering if there were really any interesting insights that came out of this work in that regard, especially considering some recent works that tend to show that even if your model is misspecified, but if you're sufficiently overparameterized, then this is kind of okay in a generalization error sense.
Yeah, that's a good question. Like, I don't have a very good answer yet. We have a recent paper on transfer learning, which is a bit kind of along those lines, because transfer learning and model misspecification, there's a lot of relation. So yeah, and I was just talking to a PhD student and suggesting it to him as a you know, kind of good topic on a PhD thesis, where, I mean, your intuition is kind of right that these techniques should be quite readily applicable to that, and we should explore what's going on in order to gain some insights. But I don't have any at this point. But yeah, that's a yeah. I totally comply to that question. We should do that, or you know, the community should do that.
Excellent, thanks. So let's all thank Lenka for her great talk. Yeah, thank you very much.
Thank you for the questions and for being here. Thanks.